Okay, magnetic friends, we got one more example here to do for you using the Biot-Savart rule. Really, like I say, it's a rule, same as I say Coulomb's rule is a rule. They might have been discovered first, but we have more wide-ranging electrodynamic laws now. So what we're going to do, although they retain much usefulness, right? What we're going to do is I'm going to do one more example with the Biot-Savart rule here, and we're going to look at a current loop. Okay, and you'd say, wait a sec, didn't we just do the current loop? Yeah, we did, but we did it in the plane, all right? And so now what I want to do is, ooh, that's not a very good looking current loop, but I want to do it at a point Z above the middle of the loop. So last time we did it at this point right here in the middle. Now I just want to go straight up and ask what's the field up here at point P. Point P. Okay, like that. So, ouch, crickets. All right, so look, we're going to give the radius of the loop the same radius. It's going to be radius A. Okay, and let's have a little bit of ds here. Same idea. It's the same essential loop. The current is moving suchly here in a clockwise. If I were at point P and looking straight down, it would be in a counterclockwise manner. And therefore, I want to look at this point over here, which is ds. Okay. ds. So right at that, all right, look, I can't draw it in perspective perfectly enough, but imagine I'm in the plane of the thing. So I'm looking at it edge on. Okay. So the current is going around like this. Okay. It's going around in a counterclockwise manner as seen from above. So now I'm going to look at it edge on here, and ds is really actually pointed out at me. Okay. So the radius is once again A, and the distance R is the distance from ds to the point P, like that. There's R. Okay, which means that R hat is that way. R hat is that way. Okay, so let's write down our Biot-Savart here. Okay, so our Biot-Savart dB at point P, and it's a vector. Come on, it's a vector, and it equals I ds cross R hat over R squared. Okay, here's the picture. Write down dB, figure out ds. Now let's take a look at ds cross R hat. So let's take a look at ds cross R hat. So what's going to happen is if I do ds cross R hat, now I went to this explanation here of I'm looking at it, say edge on, and ds is pointed at me. Okay, same as not for you. It should be pointed at you too. Okay, it's pointed out of the screen. There we go. It's pointed out of the screen. Okay, because if you look at what I'm doing, then you're going to say, no, it's pointed away from me, and that's towards me, and that's away from me. But now it's pointed toward. Look, it's coming out of the page. Okay, so ds is really this. Okay, that ds is really coming out. So if I take my right hand and I go ds cross R hat, so here's ds, and then R hat in the plane is parallel with that, is that way, okay? So ds is this way, and then R hat is kind of like that way, okay? You can't see my fingers, but they're going up towards R hat, and the thumb is pointing the little piece of dB, okay? And you notice that it's essentially at right angles to R hat, Okay, r hat is along the blue line. And so this is, if I was on the other side, I would have been going ds, and then r hat would be up, and I would have gone this way with it. If I was on the other side of the circle, right over on the over here somewhere. Okay, so what does this mean? This means that the magnetic field up here at point P due to ds is pointed this way. Uh-oh. I'm guess I'm gonna have to erase because I need this space here. Okay, so here's dB. That's the piece of dB that is due to ds. Okay, now I'm going to go all the way around the circle. Now, okay, so I've taken care of my cross product, but now I want to think about what's going to happen when I integrate around the ring. Okay, so as I integrate, and my ds comes from this side over to the front side here where my front arrow is, and then over to the 3 o'clock side, and then up to the 12 o'clock side, and then back and back, back, what's going to happen to the dB? Well, I just kind of showed you, because if I was over at the 3 o'clock and I was doing ds into the page, and then r hat would be up, and my thumb would point the field, but that's going kind of parallel with my r that's sketched in blue here. If I was over there, then the field would be, if I was over here, if ds was over here, then the field would be over here. Okay, let me try that a little bit more nicely. Okay, if ds is there, in other words this, okay, and r hat's that way, then the magnetic field is looking like that. Okay, so what this is telling you is that as you integrate around the loop, the field is swinging around in this basically ice cream cone, okay, like this. So when I start, it's over here, and then I come all the way around, and it goes all the way around like this, okay? Which means that you can see just from these two components that the horizontal pieces are going to cancel, right? Can you see that? I've got a horizontal piece going this way from the vector I just drew, and this one was from my original one going to the left. So the only thing that's going to add is the upwards one. All right, so let me extend my axis up a little bit more. Okay, so there's my z axis up, going up a little bit more. And so all I really need to do is just add the z parts of this. It's going to be going straight up. There's going to be no tilt to it. This kind of makes sense, right? As a magnetic field. Maybe it doesn't right now. It will as we talk about it. So what I'm concerned with now then is that angle there. Okay, so that's the angle that the field makes. It's bent away from the z-axis as it goes all the way around. It's that same angle, and so I'm going to get pairwise cancellation with the kind of what I'm saying are the horizontal components, the piece that are parallel with the plane of the ring. Okay, they're all going to cancel out, right? So I'm going to get a component which is going this way, component which is going this way, and these two are going to cancel. All right, and it's going to be like that all the way around. So I only have to add the upwards part, which means I need the cosine of that angle right there. Okay, as I'm doing this integration, I'm only going to need to take the cosine of that. Okay, so let's go back down here. So ds cross r hat is that thing. So as I go around, what I'm going to do is I'm just going to say, okay, I'm going to go around. I'm going to go ahead and pop the integration on here. Oh, I forgot my k over c squared. Shh. That was there the whole time. Nothing to see here. Dang it. All right, look, I'm going to get my b at point P here, and that's going to be equal to k over c squared. I'm going to get an I, and I'm going to integrate this ds cross r hat. So I need to figure out what to do with this thing. and I've got the r squared. Okay, so I've got, okay. So r squared, at least I can take care of. R squared is fairly straightforward. It's a squared on the bottom, z squared on the upper opposite leg. So r squared is just z squared plus a squared, okay? So as you look at this, what's going to happen here is that I want the ds cross r hat to be pointed in the z direction, okay? So my field is ultimately going to be pointed that way, okay? That's B. When I add them all up, so ds cross r hat is really, it's a little bit strange this time. It's really a ds, and it looks like a cosine instead. Cosine of that angle. Okay, because that's the component that I need to take as I kind of pull it around in the ice cream cone fashion, right? As I go around, that's the adjacent side right there. Okay, there we go. Okay, so there's that. The question is, what is that angle? Oh yeah, so we got to look at this. All right, look. The field makes a 90-degree angle with R, this blue R here. So this thing right here, ding, ding, that's a 90-degree angle, which means this angle must be 90 minus theta, right? Because that's a full 180 from up there to down to the dashed line. So I've got theta there, I've got 90 there, I'm going to have 90 minus theta here, which means that this angle here, right here to here, is also theta. So the cosine of theta, I could write that as adjacent over hypotenuse, A over R, which is going to look like A divided by the square root of z squared plus a squared. So let's get that. Okay. All right. So you're going to say, wait a sec, wait a sec, wait a sec. What are you talking about? Isn't a cross product always a sine of theta? Well, it could be. It depends. So the cross product is just like the dot product. It depends on the angle between the two vectors. Okay. But what's the angle between these two vectors? The angle between ds and r hat is 90 degrees, right? Look over here at this picture right here that I drew with ds pointing out of the page and r hat going up at an angle. That's a 90-degree angle. All you got to do is kind of look at it from this direction and you'll see that's a 90-degree angle, right? I got one this way and I got one in the plane. That's 90. So there is no sine of theta regarding the cross product. Okay, so the cosine that I'm sticking in here, that's not because of the cross product. Okay, the cross product is 1, or the sine theta is 1. The cos, as I'm trying to motivate here to you, is actually like, it's from this thing that we've done before with the electric field where I don't need to take all the components, because as I go around, I can see these two are going to go away. So I'm doing this as part of the integral. Okay, I'm doing a symmetry argument here to say I don't need to take the entire b, I just need the upwards pointing b. All right, so that cosine is not a cross product issue. That's an integration issue, because when you add this and add this, these parts go away and this part's left. So let's make our lives a bit easier and not worry about that. I can't leave this ds cross r as a scalar on the right because that's no good. Oops. And so I did not want to do that. I want to do a z hat here because the field's pointed straight up the z-axis here. Okay, so what I'm going to end up with here is this thing, once again to the 3/2, and I'm going to have an A on the top. I'm going to have a DS, and I got a Z hat. And now I got to choose my limits. What's my limits? Limits. It's the circumference of the loop again, because that's where the current is. 0 to 2 pi a. All right, now we look at this integral and we go, oh, not another one of those weird things. Sorry, the internet must have cut out there. What part of this integral is something that I would integrate with ds? And the answer is none, right? There's not, z squared is not part of this current loop. A is a constant. It's kind of part of the current loop, but it's a constant. So I'm going to get I get Kia over c squared. I'm going to have this 1 over z squared plus a squared coming out, because that's not going to get integrated. I'm going to have a z hat, and then I just got the integral of ds, because there's that's the integral on the actual current carrying part of the wire. So happy days. And that's why I start with the worst ones. Because then by the time you get to this, you're like, oh, thank God, it's not one of those weird ones. No trig substitutions. So what's going to happen? This integral just turns into a 2 pi a. And that's going to go a squared on the top. I'm going to get a cancellation with some of the 1 over 4 pi epsilon naughts I'm going to get. So I get a half down there. I'm going to get an I. So what do I get? I get I a squared divided by 2 epsilon naught c squared. And let's just knock that off here. And now I've got 1 over this stuff. And it's in the z hat direction. I think that's it. Kind of makes your heart warm, because you got that 2 epsilon naught c squared in the bottom, which is something you had in the other current loop, right? We had that in the other current loop where we just did it in the plane, right? We had a 2 epsilon naught c squared in the bottom, and we had, what do we have, an ia squared? Well, I guess it turns out the a was on the bottom in that case. Whatever. So good times. One thing that I would ask here is, again, what if we were in the far field? Okay, what if we were in the far field? Let's take the far field limit, because this is such an important physical piece. Just as we asked what was the situation with charges, as I get really far away, it's going to be point charge looking if it's a finite size charge. Well, what if I'm in the far field limit here in this thing? What do I expect it to look like? It's a current loop, and it turns out, you may not realize this, I'll sketch it out for you. A current loop like this is going to have a B field, which looks like this. Okay, like that. Wow, that's horrible, but that's okay. And what does this look like? Does this remind you of anything? I'd hope you'd say it'd be looking like a dipole. Okay, I hope you'd say it'd be looking like a dipole. And we're right here on this very middle one here, and we're far enough away. So what does a dipole field look like mathematically? Proportional to 1 over r third. Okay, 1 over r third. let's see if we get a 1 over r third here. In the far field limit, the far field limit is z much, much greater than a, which is to say my small quantity number is a over z. That's got to be much, much less than 1. All right, so I'm going to say b at point, oh, not at point P anymore. It's at point really big z is going to be equal to I a squared divided by 2 epsilon naught c squared. And I'm going to factor off a 1 over z to the third out of this thing in order to get my 1 plus a over z. That's going to be squared underneath the 3 halves. Okay. I mean, I could make it, I can stick the z hat in there if you like. Oh, I mean, we know it's that way. All right. So let's just forget about that for a sec. Okay, so now I'm going to hit this thing right here with the binomial. And that thing is going to be approximately 1 minus 3 halves times a over z squared. Okay, right? Okay, so that means now I've got this thing, which I can say is now approximately equal to all of this stuff, which I'm just going to say number in the parentheses here, times 1 over z to the third. All right, that hits the 1 minus, now I get a 1 over z to the third, and then I get it hitting this 3 halves a squared over z squared, like that. But a over z already was much less than 1, and a squared over z squared is going to be really small compared to 1. So we're just going to knock this term and say this is ignorable. Okay, that turns ignorable. So then it turns out to be approximately I a squared divided by 2 epsilon naught c squared z to the third. And there is your z to the third. That's your dipole field. So indeed, that checks out. And don't forget about that binomial. It still is useful. Far fields, near fields, anything. Okay, it's a really useful tool to have in your kit. All right, for making quick approximations. Okay, so that is pretty much that in terms of the Biot-Savart and how to handle this crazy IDS cross R hat underneath an integral. Honestly, I cannot stress it enough. Learn to draw these pictures. Get those pictures really figured out. Because if, at least for me, if I am looking at the right-hand rule, I need to know, okay, I got a DS, I got an R hat, it's going this way, and I got that, it's going that way, and if I go around here, it's going to go, right? I need to be able to see where these things are. So that's my advice. Draw that picture, get the DS dealt with, figuring out where it is, get R hat, figuring out where it is, do the cross product, get that out of the way so you don't have it sitting around in an integral making you freaking out about how am I going to integrate this cross product. Okay. And then what else? Oh yeah, far field limit. So this dipole, over here, this dipole thing is pretty much what you expect almost all the time from any type of loop type looking thing, right? Because they're magnets. A current loop is basically a magnet. It has the exact same field. All right. Now, as we go further and further into finding magnetic fields of kind of strange and wonderful looking situations, we'll get, just like we did with the Coulomb fields, like we're going to get different fields. But current loops, that's like the point charge thing, right? If you had a finite charge and if you got far enough away from it, I'm going point charge, baby, right? I know that. And it's the same thing with a current loop. Anything that's loopish looking, you go far enough away. I got dipole. Okay. This is a dipole field. So 1 over r to the third. Okay. Good. So we got that taken care of. And our next task is law number 4. Is that right? Yeah, it's equation number 4 in the Maxwell equations. So I'll see you then for some more funsies. Bye now.